Hi and welcome to video 3 of this statistical inference topic. We're going to be talking about distributions of sample means, and this topic of course is Unit 4, Topic 3 of the Specialist Maths curriculum. And it's going to be important here that if you're watching this that you have covered that Unit 4, Topic 5 of the Mathematical Methods curriculum will really be helpful here. So we're going to talk through using Cambridge as our guide for order, just to help you working through that textbook reference. But it's a little bit linking to methods, looking at some new ideas. So to start with, it's a bit murky, and we'll try and build that deep understanding through what we do. And I'll break this up into a few videos. So this will cover 15C, D and E. Just a reminder, first of all, though, some of our concepts you need to remember. The population is the set of all possible members in a group. So it could be a population of people, but it could be a population of cars, and we're measuring a statistic off a car, or koala bears, or distances between towns, or whatever. A sample is a subgroup of the population, so that's where we take a small group of that population, and usually we do something statistical and assume it's representative of the population. A random sample is where we take that small group randomly. Population mean is mu, and these will be important, mu, whereas a sample mean is called x bar in this case. And I'm going to just reference the work that we've done with methods and try and explain the difference between the sample mean that we'll be using in specialist mathematics and p hat, the sample proportion that we use in methods. And I'll do that in a second. Now the sample mean x bar, so this is, you'll note here the difference between this x bar, which is a lowercase x, sample mean of a set of a randomly chosen set or sample, and that's just basically a point estimate of that mean, whereas a sample mean distribution is when we collect a lot of different sample means and we look at how that distribution might lie. And it can be seen as a random variable, and it's called the sampling distribution. So it's always important to have these summary of concepts in the back of your mind. Now on page 618 of the textbook you're using, and I'd strongly suggest that after you've gone through and done some of this work, that you go back and read those and just see if your understanding has adapted with these as we go. So maths has done this to us, and this is where it's a bit tricky. In methods we use p hat, and p hat is x over n, and it's called a sample proportion. Whereas in specialists we use x bar, and it's a sample mean. They have different names and they have slightly different meanings, and so we have to make sure we get it right. The good news is that really you're not going to get a p hat question in a specialist exam, and you're definitely not going to get an x bar question in a methods exam. So there's that difference there, but they are quite similar. So here's my best take on explaining it to you. P hat, which is the sample proportion for math methods, is a binomially distributed or calculated variable. So p hat is built on the idea that we just get our x by counting how many of the objects or the items within the sample have a certain characteristic or attribute, and divide by the total number in the sample. So in this case you might be you might say, 17 people in a photo with 30 people are wearing a hat, and we get a population a sample proportion by doing that. And 17 is a whole number. 17 represents just the counting. So this is discrete and binomial. Whereas on the other hand, in specialist maths we do the sample mean. But in this case the sample might actually be, well, we're measuring, we're just taking randomly the lengths of 10 plants, or the heights of 10 plants. And so we have these numbers at 10.1 and 11.3 and 9.7, etc. And we take a mean by doing the sum divided by the number that we took. So it's a mean of potentially a continuous data variable, but it could also be a mean of a discrete data variable. But in this case it would be, say, the number of students in classes at a school, and you take a sample of classes and then you add up all the students in that sample divided by how many classes you took, and that would be a sample mean. It's a little bit more complex in proportion, because the proportion here is just counting up how many classes have a certain attribute. So in that case you might say how many classes in a school have more than 15 students, and then you count that up, and 11 out of 15 of them did, so that's our sample proportion. So there's a slight difference, and I think that at the basis it's to do with the fact that the sample proportion is a counted value. you've counted how many things meet a certain criteria, whereas a sample mean hasn't really got anything to do with counting necessarily. So there's the difference, but they are quite similar. So just keep that in mind as we go. Now, if we take a sample, we can calculate p hat. We know that. This is a reminder of our working methods, and important to know. Now, 15C, and it's going to be important that you see this, is about generating samples from your calculator. And I'm going to show you a couple of other sources for generating samples as well. But I'll show you a calculator example now. This stuff is in the textbook. So we've got, again, this idea here, generating using statistics, probability, random normal, random binomial is rand bin, or just a random integer, rand int. So we can do this stuff to collect data that we want to collect, and then we can go, if we've done this in statistics and we've collected our data in a statistical list here, well, then we can set up our graph function as well. So we click on that set menu, and in the set menu we can set graph 1 or graph 2 or graph 3. So say graph 1, set it up as a histogram, set it up using list 1, make sure that you've got all those settings right, and then go into here, and you'll get a nice graph of the data, which is great. So you can do that, and it's pretty easy to do. You can also download, we can do it in the spreadsheet, which has got its extra benefits as well, but it has got some limitations. So you've only got columns A to Z, so you can only really take a sample of up to 26, or if you move down you can take a sample down to 26, but then you can only have 26 different samples. So we've got some limitations here, and there is a program which you can download, and you're welcome to do that. But my big point here is that, and it's in purple here, it's really unlikely that in an exam they're going to ask you to take a sample. They may provide a sample for you and ask you to do something with the sample, but it's very hard for examiners in an external exam to ask you to take a sample and then for them to be able to actually check that sample and have everybody coming up with a different sample. So that seems pretty much impossible to me. So actually being able to sample in your calculator seems an unlikely requirement. But nonetheless, I did write an example. When I roll the dice, the expected value is 3.5. Now you might remember why that is. If we go right back to chapter 15 or to the binomial distribution stuff from math methods, the expected value of a discrete distribution here is the sum of all of the p times x values, which in this case was 1 times 1, 1 times 2, 1 times 3, 1 times 4, and then we get that sum we divide by n. So if we rolled the dice 6, we would expect to get over 6 rolls a 1, a 2, a 3, a 4, a 5, a 6, and it comes out as 3.5. But you have to set out your probability distribution table, and if you do set out your probability distribution table, we don't need that divided by n, because our probabilities will all be 1/6, and then x will be 1 to 6, and so you're going to end up 1/6 times 1, 1/6 times 2, 1/6 times 3, which is 21 over 6, and that's also 3.5, depending on how you do it. Use a calculator, or use our calculator, to inspect a series of samples of 50 dice rolls as a histogram of p hat. So I've done this using the method shown before. Comment on your results, and here's one I made. So I used rand int 1 to 6, and I've collected a list of 50. So you can see here I rolled a 1 in the first case, a 3, a 6, a 4, etc, etc. Then I've done my one variable statistics, and I've got in here my x bar 3.195, a little bit lower than the 3.5 I'm expecting, but that's okay. And I've also got my standard deviation here. This is a sample standard deviation, but there doesn't seem to be much in the way of requirements for us to do that. And also you can see I've done 200, and the question said 50. So I'm not really sure why I did that. But anyway, I've taken a sample of 200, so that's exciting. But then I've done this. I generated 100 cases of this sample. There they are there. And I put them into this chart. So 3.5 is our expected value, which is here. And I generally got 3.5 mostly, but I did get that one there, which I'm guessing is 3.2 to 3.4 the most. I got 3.6 to 3.8 a lot. It dropped off here. That's a little bit of an abnormality, but you can see it kind of follows this normal distribution. We could use that normal distribution to estimate values from here. In this overall histogram, I've got fairly close to 3.5, but my standard deviation, you'll see, has actually gone down. So my standard deviation for just a sample of 200 was 1.66, but my standard deviation for 100 of the sample mean has gone down to 0.575, and we'll talk a bit more about why that is as well as we move forward. So there's the example in the calculator of starting with dice rolls, getting the mean, and then I got my calculator to look at doing that 100 times. Now let's have a look at another resource here. So if you're on my OneNote, you'll notice here there's a link to this resource. You can have a play around with it, and it's worth having a play around with. It's a really good statistical website, which you should be able to see up in the screen now. So just having a play around with this, we can have a look at an animation. Now we can set this up, our population, to be whatever we want. So I might set it up to be uniform, and so this uniform distribution, that's kind of like our dice roll now. Of course, this is a dice with 0 to 32 on it, so I haven't set that up differently. I've got a mean of 16 though. And it goes up to 32, and it's set up the parent population, standard deviation, etc. But I'm not too worried about that at the moment. What happens when I randomly select 5, and then you'll see below I do the population, also the sample mean as well. So I'll animate this to start with. So it's randomly selected those 5 and give me a mean here. And what if I do it again? Now, so you'll notice here what this mean is doing is it's taking the edge off our results. This was a great example. These randomly selected ones, the first one had a 32 in it, the second one's got 2 zeros, which seems pretty unlikely. But remember, the 0 is just equally as likely as this one here, which is 28 or 27. But this, because I'm taking a sample of 5, these are taking the edge off that. So I'll do one more animated one. It's a little bit more central, and you can see I'll get a nice central mean, around about what I expect. So what I can do now is I can just automatically generate 10,000. So I'm just going to quickly do that. And it comes here, and you can see what's happening is I get this normal distribution, exactly what I expect. 10,000 is a lot. So I'm getting a pretty perfect normal distribution at this point. But it's quite spread out. What if I do 100,000? Now, when we increase the number of samples that we take, we should find that the standard deviation starts to go down. So my standard deviation is actually hanging around at 4.26 at the moment, and it might be at the point where I've done too many for it to affect it. But we can see here we're getting a really nice normal distribution. Now on this website you can play around and model different things, which is nice. So it's certainly worth having a play around with that, and we'll have a look at this more in class as well as we move forward. So that's it really for this lesson. It's just worth considering what happens as we take more samples, what happens as our sample size increases, and what does this mean for the ability to estimate P. Now we're on 15C, there's 4 questions, but they're all very similar and they're all about taking samples. So my suggestion will be just maybe do one of exercise 15C and see how you go. Have a play around with another one if you want to, but if you can do the one, you're probably in a good space. All the best.